In our journey to grasp a radical new understanding of space and time, it's crucial to really understand where we are starting from: Newtonian space and time. By delving into our intuitive notions of space and time, we can lay the foundations for exploring the transformative concepts that lie ahead in special relativity. So what is Newtonian space? Newtonian space acts as a background upon which objects are placed. It's a background in the sense that even if we took all of the objects in the universe out of it, there would still be space. Space gives us a reference as to where objects that are placed into it are. Space comes with its very own notion of distance. If we place an object over here and an object to the right of it, then the amount of space in between them tells us how far apart they are from each other. It's very useful to place coordinate systems or reference frames into space, as this helps us count how far away things are more easily. However, this is not strictly necessary, and there is still a notion of distance even when we don't place coordinates there at all. Crucially for our purposes, the distance between two objects in Newtonian space does not depend on how fast we travel relative to them. This is very intuitive and aligns with our everyday experience. Newtonian space also exhibits a very interesting feature, a kind of symmetry. If we take everything out of the space, it suddenly becomes impossible to tell which direction we're pointing in. Furthermore, if we rotate the entire space by 30 degrees clockwise, space looks exactly the same. We can do this about the x-axis, y-axis, and z-axis. Nothing changes. Because of this, space is said to have three-dimensional rotational symmetry. For the mathematicians out there, Newtonian space is invariant under global SO3 transformations, but don't worry if you don't know what that means. Even though space itself doesn't change when we rotate it, objects that are placed inside of space might. Consider Newton and Galileo placed apart from each other. Space gives us an absolute notion of how far separated they are from each other, and we'll call this distance L. From our reference frame, which is aligned face on to Newton and Galileo, we see that they are far away from each other. However, if we rotate our perspective whilst keeping them still, then their separation appears to get smaller and smaller until suddenly Newton and Galileo are right on top of each other. Of course, the two objects, Newton and Galileo, will claim that the distance between them hasn't changed at all and was always L. In fact, imagine that there's someone near us who rotates with us. We'll call them Alice. Newton and Galileo will actually claim the distance between us and Alice gets smaller in exactly the same way as we rotate. The separation between two objects in space can appear to increase or decrease depending on how we are rotated. This is a peculiar feature of rotations and of space, and will prove vital to us later on. Now, what about time? It's very common when people talk about special relativity to say that time is the fourth dimension. However, what people usually imagine after hearing this is a bit misleading and is actually already a feature of Newtonian space and time. Newton's notion of time can be thought of as a length that is at 90 degrees to space, through which every point in space travels along at the same speed. Don't worry, it's impossible to fully imagine this. I can't, Einstein couldn't, and neither can Neil deGrasse Tyson. All of us are only able to visualize a maximum of 3 dimensions. Instead, we have to consider at most 2 dimensions of space, and then draw the time direction at 90 degrees to this. In fact, for our purposes, it will actually prove most efficient to only consider 1 dimension of space, along with the dimension of time at 90 degrees to this. Newton's idea about how this direction, time, behaved were as follows. All objects, regardless of how they are rotated or their trajectory through space, travel through time at exactly the same speed. If we're still moving, not through space, but through time. As we move through this length with a constant speed, we evolve. Alice, who is moving through space with respect to us, also moves through time with us at the same speed. In Newton's world, nothing you or anyone else can do will alter the speed at which another object travels through this time dimension. Time is absolute. Just like in space, we can imagine a distance travelled through time. Consider our future selves at this exact time tomorrow. They're a distance of a day separated from us in this time dimension. In fact, the notion of distance in time is fully ingrained into the English language. If you're lying to yourself about your train showing up on time, you might say, "Not long now." If you're procrastinating over homework, you might say, "But it's so far away." The key feature of Newtonian space and time that is vital to grasp is this. There is no way to rotate between the space direction and the time direction. They are completely independent of each other. As such, there is no possibility of 2 people disagreeing about the distance in time separation between 2 events, in the same way that observers who are rotated differently in space are able to disagree about the spatial separation between 2 objects. Furthermore, if 2 events happen at the same time for one person, then because everything travels through time at the same rate, everyone is also on this time plane, and everyone agrees that events happened at the same time. Finally, it's essential to realize that Newton already knew about the first experimental fact that we talked about in the first video. As such, the space that he created fully incorporates this and is completely consistent with it. We will now try and find a mathematical expression that tells us how to transform from one frame of reference moving at a constant speed to another frame of reference moving at a different constant speed. So go and grab a pen and some paper and try and follow along with me. Imagine that we have Alice, who is standing by the road, and Bob, who is driving on the road in a car towards the right at a velocity v. Alice uses a coordinate system, S, in which she is still and exists at the point x is equal to 0. Bob uses a coordinate system, S prime, in which he is still and exists at the point x prime is equal to 0. How do we go from using x coordinates to x prime coordinates? The answer is with x is equal to x prime plus v, the velocity, multiplied by time, t. This can be a bit tricky to understand, so let's unpack this. The equation basically says this. In the frame of reference where x coordinates are being used, all x prime coordinates become bigger numbers as time progresses, and hence move to the right as time moves forwards. Bob exists at x prime is equal to 0. As time goes forwards, Bob, and hence the position of x prime is equal to 0 in the x coordinates, moves to the right. This seems to agree with our equation. If Bob moves quicker, then in the same amount of time, he will move further to the right, which also seems to agree with our equation. And finally, if we go to Bob's frame of reference, where he is not moving, then we should appear to move to the left with time. By rearranging the formula, we get x prime is equal to x minus vt. We see that as time increases, the formula does indeed show that in the x prime coordinates, we move to the left at exactly the same rate that Bob moved to the right in our coordinates. If we draw this in the time-space axis, we see Bob moves in a straight line that gets steeper the bigger v. From his perspective, it is us who are travelling at a gradient through Newtonian space and time. Because the speed at which everyone goes through time is the same, we do not need to change our notion of time, and so both t's mean the same thing here. If this isn't completely clear, feel free to pause the video and think about this for a while. Now that we have a clear notion of Newtonian space and time, along with the two experimental facts that we need to make consistent with each other from the previous video, we're in a perfect position to discover how Newton's idea of space and time must be modified, along with the crazy implications that emerge as a result of this. Special relativity.